to grab it here again. So now we're continuing on Rust, and now we're going to have a little look at ownership, and we're going to follow the established routine. So we'll have a look at it in terms of code examples. So anyway, we'll start. Before we get into the into Rust, then I think it would be useful to reflect on how a few other programming languages actually handle similar type of operations, which is creating a variable and then referring to something. So let's take Python first. So here you have a very simple Python line. So basically this says that S is equal to a list, and the list has 3 elements in it. And if we actually have a look at how it then creates this, then you have the S, which is actually going to be now a reference to a PyList object, and it has some properties. So here we see where it starts. So there's one reference from here to here, and then it has a list and capacity, and then it actually makes a reference to the start of the list elements, and then the list elements actually contains a reference to the actual element, and then the element actually contains a reference to the actual string, and then this is repeated 3 times here. And here we see where it has the reference count, which is now 1. Okay. Now, what happens when you take this list and then you assign it to 2 other local variables? Well, what happens is that it doesn't copy the list. It actually increases it makes references to from T to S and U to S, and then the PyList object's reference count is incremented to 3. So now it knows that it has three references pointing to it. So that's how Python works. So as a summary, so Python uses a copy pointer and manage reference counts strategy. So that's the summary. So let's have a brief look at C++. So here's a simple example. Vector of strings, same structure. And then you have S, and it points to a stack frame, has a capacity of 4, use 3, reference to heap, and in the heap then you have the actual individual items, and then they have their references to the actual string then. So what happens when you actually do this type of operation where you're doing an assignment to two other local variables? So what will happen in this case, that C++ will actually make a complete copy of the structure and then have a pointer to that new structure from the individual variables. So anyway, as a summary, so C++ uses a deep copy everything approach, and then I'd just like to note that in programming there's always a way. so yes, in C++ there's a ways to mitigate this, but if you just take the raw model, the raw default behavior, then this is how C++ does it. So now have a look at what does Rust do then. So let's have a look at the summary first, actually, in this case, and then we'll go through a few the examples. So Rust uses a concept of unique owner and transfer of that ownership under predefined conditions. Okay, and then when the ownership gets transferred, the original owner not only loses ownership, but reference to the target object in question. So let's have a look at an example and you'll see how this actually works. So here we create a Rust vector, also 3 elements, just to keep it simple. And basically it builds it in an identical fashion as C++ basically does. and then you say you assign it to the next local variable. And then what happens then? This is where it gets interesting. The original S variable is now uninitialized. So the ownership has been given to _t, and then S loses its reference to the vector. And then, of course, it just inherits. It's just moved over the reference. So now T points to the exact same structure. So it's no different there. As I said, the S is now non-addition, cannot be used. And then what I've done is in this code that in several places I've included the actual line that that will fail if you actually try and build such a structure, because that's important, because then you can actually so when you come to this code, then you can actually you can just take away the comment, and then you can run the build, and then you see what the compiler will spit out. But I've also added it as a comment here, so you actually don't have to run the code to see what happens. But in this case, if we say, okay, I want to assign S to U now, and you know S is uninitialized, so then you actually get a compile time error, and this is very typical to Rust behavior. That Rust is it's basically a compile time check everything language, and the language is structured in such a way that the compiler can check at compile time that everything is in order, so that you minimize the amount of mistakes at runtime or bugs and side effects. So, but this can be a bit shocking. So this doesn't feel good. So I put in here, I hate this. Give me the same behavior as in C++. So this is basically copying the deep copy method. So you have your vector, and then you use the clone method here. So basically it copies it. So then T gets its own vector with a reference to it, and then U gets its own reference to a new copy of the vector. Now, ownership moving on doesn't only happen when you do variable assignments on a local scope level. It also happens when you, for example, return a function value from a function. So this is an example where you say that composes is a new vector. So in this case, what happens is the ownership gets transferred from rect to new to composers. And then it can get a little bit more complicated when you have, like in this example, we have composers push, and then a structure person with the individual values. That then you can have multiple instances of ownership change. Returning values from a function, so JSON to string returns a string instance, reference, constructing new values, string instance to name, passing values to a function person, vector push method. So it's like several you can have several layers of ownership change. And move and control flow. So it's a simple example here. We say x is a vector, and then c is a condition. So if c is, it doesn't really matter, but the idea is that it will call one or the other function, and it will use this vector as a parameter. And when it does that, then basically the default behavior is the ownership is transferred to the function in question, and then if you try and execute or have this line, then the compile will fail, because basically it's either of these will take ownership of this, and it actually no longer exists when it exits the control. And then here's another example where things will fail. You have a vector, and then when you do a loop and then you're passing the vector as a parameter to the function, and it does the first iteration of this loop, it will actually steal x. And actually that's wrong. It should be x2. There we go. So then it'll steal x2, and then when it does the next loop, then it'll fail. But basically, you can't compile this either. So if you try and compile this, then it will the Rust compiler will tell you that that's actually what's going to happen. But yeah. And this is the good thing, good or bad thing is that at compile time it will be checking these types of things. Okay, use and index content. So we create dynamically a vector. So it's basically a vector of elements 101, 102, 103. Using push. So this is just standard code. But then what we think we'd like to do with this is that we would like to extract some values out of this vector. And the problem is that when you then try and extract a value out of the vector, then it's basically the code is trying to take ownership of a specific element. And then there's the rule that says index content elements cannot be uninitialized. So because basically the part of the rule taking is that there's only one owner. So when you transfer the ownership, then you uninitialize the source. So that won't happen in this case because it's, as it says here, cannot move out of index of vector string, because it would actually need to uninitialize it to actually do this. But this is also, like I said, compile time. You'll get everything where I've commented out the lines of the Rust code. Then you even without compiling it, you'll know that this is code that if used will fail compiled. And in most cases, or actually in all cases, I put already put in the error that you'll get. So how do we actually then go about getting some values out of the vector? So here I've put in some examples which don't trigger this ownership transfer, which then doesn't trigger the uninitialization of the source. So you can actually just pop a value off the end of the vector with this pop function, and then you say unwrap to get rid of the result wrapper. Move value out of the middle of the vector and move the last element into its spot. So then swap remove can be used. Swap in another value for one you're taking out. This is a little bit more advanced and actually does it directly as a with the replace, like as I wouldn't say low level, but it's a direct memory access to the storage. Oh, let's have a look at this special case. Now, if you actually want to make an element removable, then you can actually use this type option. And the way this works, I've made an example here. So we define a dog with a structure, and we say that the name is actually not a string; it's an option with of the type string, and then birth remains the same. And then we create the vector of dogs, so I only put one dog in there, and now you can use this take function to actually take that element out, and it's going to be wrapped with the result wrapper. So then we use unwrap to actually get access to the main name. And if you then print out the element value index 0 name, then it will actually report none, because it's actually been set to that element has been set to non-initialized. But this trick enables you to actually extract values. It's like remove values from the structure. In this case, it's the structure, but it will work with other constructs also. So moving on, copy types. The exception to moves. Now they've just been going through moves and how it works, and yeah, how complicated that is. And then they suddenly say, "Well, but we've got an types that are exempt from that rule." And yeah, basically these are the like a little bit more simple and lower level types. So that's like the machine integer and floating point numerics types, char and boolean types. And then it says like a few others, so it's not exactly clear. Yeah, a tuple or a fixed size array of copy types is itself a copy type. So this is one of the problems that if you create a tuple, it's not by default copy type until you actually include only those types that are also that support copy, and then automatically the tuple will be a copy type. And then Rust has some kind of a low-level rule. Only types which simple bit-by-bit copy suffices can be copied. So that's what they use as the platform rule. So here we have a simple like num1 is 36. So this is a simple copy type. So here we copy it over. So then it will not move the ownership, and then it will not kill this num1, so that will still exist. And what's interesting, that you can actually so if you're going to actually enable a copy on the higher level object, which contains copy type objects, then you actually need to add this here. So you say copy or derive and then copy. For example, in this case it's a struct. So in this case we create one here. And then when you do this assignment, then it's going to actually copy the whole struct into label 2. And if you would actually like to have the Python's reference count model, then there's actually there's a way to do that. So then you have shared ownership of references, and that's the RC and ARC features. And then I just put a simple example here. So when you're using RC, then basically you wrap the, in this case the type string, you wrap it with RC. And then you say RC new string. And then you can, when you use these clone features, then it actually creates shared ownership and doesn't copy stuff. Or I think this will get a bit complicated, is that a value owned by the RC or ARC pointer is immutable. So if you would activate this line, then it would actually fail. So you can't actually change, for example, that one. And yeah, so then you get these kind of cannot borrow data on an RC as mutable. And then of course the other thing is that when you're talking about ownership rules, they still apply to the actual top level RC and ARC pointers. So they still follow the ownership rules. And then ARC is exactly the same syntax. And the difference between RC and ARC is that RC is not guaranteed to be thread safe. ARC is. So if you're making parallel programming or something, then you should use ARC. And the compiler will probably tell you that much when you start building that kind of code. And I have to say that there are additional methods to enable interior mutability and protect against reference counting loops, and I'm not covering them here, so I just stick to the basics. So anyway, might feel confusing in the beginning, but I mean the key message to take home is that when Rust has this, just keep in the back of your mind that Rust has a mechanism of ownership, and when ownership gets transferred, it actually wants to kill the source from which it got the ownership from. And that will save you a lot when you're like mentally thinking about program structure, or why am I getting a certain type of error. That it's the ownership. I need to keep an eye on ownership, because it's very easy to hack Pythonic or C++ type code, and then when you try and compile it, then you get lots of this ownership related garbage coming up. So if you want to, Rust is a bit that if you want to play the game, you got to follow the rules, and that means up front. Rust will, for good or bad, it won't compile garbage. So if you create a bug-ridden application, C++ and C, and to a certain extent Python will happily compile it, and then you will see runtime when things go horribly wrong. But Rust really, the ownership model is strict. So if you try and break it, then it will give you you will not end up with an executable. So some people think that that's just super annoying, and you know, the programming language itself getting in the way of productivity. But to a certain extent, the amount of time that one spends locating problematic behavior in C and C++ compared to actually this model where most of those things are cleaned out even before you get an executable, I think that I could vote for this model instead. Anyway, hope you enjoyed. See you in the next one.